Hello, everybody, and welcome back to another episode of the Math and Physics Podcast. I am your host, Parker.
And I'm Ray, and we welcome you to episode 13 of the Math and Physics Podcast, where today we're going to be talking about cool geometric shapes and interesting geometric facts about manifolds and basically the universe. So let's begin.
Every single episode just ends up being about the universe.
The universe.
I just wanted to start off with the simplest shape and the very, I guess you could say the shape with the least vertices that is possible in 3 dimensions, and that is obviously the triangle. And there are a lot of super interesting properties that come with this super interesting shape. Mm-hmm. So in elementary school, or no, not even, what am I talking about? This is like middle school / high school. We learn a lot of these theorems, such as like the sine, is it called the sine theorem? Where it's like sine A over A equals sine B over B.
That's sine law.
Sine law, right?
That was not elementary or middle school.
I know.
That was high school.
No, that was like middle school.
A sine law was high school. Sine A over A equals sine B over B equals sine C over C. That's high school.
All right.
That's like grade 11, grade 12 stuff.
Anyways, there's the sine law. There's also the cosine law. And then they try to teach you trigonometry, which has the word trig in it, and it kind of tricks you into thinking that trigonometry is about triangles. But in reality, the more you get into math and calculus, you realize that trigonometry is just all about circles. It can be applied to triangles, but it can also be applied to every other shape. But, trigonometry emerges from the properties of a circle.
Yeah, that's true. From the original unit circle, right? That's originally where all the sine, cosine, trig came from. Because not a lot of people actually think about this. Even though they know it, they don't necessarily think about it. That the unit circle, or like the 4 quadrants on the Cartesian plane, are basically originally where you can say trigonometry started from. Because we have, the CAST thing, where on the first quadrant, it's all of them are positive, negative, stuff like that. So, or at least that's how I think it originally began, because that makes a lot more sense, because we can generalize the unit circle to basically any object. But a triangle can't really be generalized into any object, right? So I think that's why you could say that it would be a little bit easier to generalize it using the unit circle.
Right. And if anyone's listening and they don't really know what like sine, cosine, and tan is, it's actually really easy. If you just follow the path of the circle, starting from 1, 0 on the Cartesian plane. If you just follow the path, sine is just the height of your point, and cosine is just the distance from the y-axis. So like, I don't want to say the length of your point, because that doesn't really make sense, but it's the x-coordinate of your point. And so it creates this wave pattern if you draw the graph for each one. And these wave patterns can actually be applied for, in tons of fields, such as, quantum mechanics and
wave dynamics too.
Yeah, and obviously in classical mechanics, when you're doing rotational dynamics or just like rotational motion and things like that.
Yeah, so I think it can be pretty much used in a lot of places, and that's where, trig is useful in general. Because pretty much any object, even if you take like a square or anything with greater than 3 vertices, can be taken or generalized as a triangle, right? Because a square, for example, you just put a diagonal through it, you get 2 triangles, right? And that can be pretty much done with any shape, any vertices, any sided figure. And that's what's, I think, cool about triangles being like the fundamental 3-dimensional shape, because from triangles, we can, move on to higher and higher, shapes. But the interesting thing, as I already said, is that higher shapes can be broken down into just smaller triangles.
Right. So it kind of all stems from the original, quote unquote, original 3-dimensional shape. So yeah, those are shapes in 3 dimensions, but there's, or I guess 2-dimensional shapes that we can analyze in 3 dimensions. But there are also other interesting shapes, which is going to be like the body of this podcast. So the first one I wanted to talk about is the Mobius strip,
Mm-hmm.
which is actually a two-dimensional manifold that is embedded in 3 dimensions. Okay, so if you don't know what a Mobius strip is, imagine you have like a rectangle and then you twist one side and then you connect the two ends. So basically what happens is that you can draw a line on the Mobius strip. If you start at one point and you just go along the strip, you will end up drawing a line on both sides of the paper that you twisted and connected together.
I think something a lot better would just be to simply search up online Mobius strip because, well, the problem with the podcast is obviously we don't have any video, so we can't show it to you. And for this entire podcast, I don't think it's just for Mobius strips. For pretty much this entire episode, it would be a lot better if you search up all of these shapes that we're going to be talking about because it's kind of hard to describe it in words without having like a figure to talk about with it.
Mm-hmm.
Yeah. And before you continue on, I want to tell a joke, a very funny joke,
Okay.
an extremely funny joke that I heard from the Big Bang Theory. Okay. And it goes like this. Why did a chicken cross the Mobius strip? To get to the same side. Boom!
To get to the very same side, because there's only one side.
Yeah, so I just thought that joke would be perfect with what we just spoke about.
Yeah. So, one thing that's kind of cool is that as a 3-dimensional being analyzing this object, it appears to be a 2-sided object, right? Like I can put my finger on one side and I can put my finger directly on the other side. And, I can follow those like 2 opposite points along the strip at all times. And I can kind of define 2 different sides of the object. But as a 2-dimensional being on that strip, it would basically seem as if you are just going along straight forward forever and in an infinite loop. And you would never know on which side you would be on at any point because it's just like walking. It's like a human walking around a ball. There's no beginning or end or top, bottom, or left and right. It's all the same.
And just making sure, the Mobius strip, as you said, it's a 2-dimensional object in a 3-dimensional manifold, correct?
It's a 2-dimensional manifold in 3-dimensional space.
Oh, exactly. That's pretty much why I was trying to get the... Yeah, okay. Makes more sense.
Yeah. Okay, so continuing on from the Mobius strip, we have the Klein bottle. And, I can't really explain this with words as well as you can just Google it, like we said earlier. But if you take 2 Mobius strips and you attach edge to edge the 2 Mobius strips together, you will get a Klein bottle. So this is just a shape where the inside is the outside at the same time. Just like in the Mobius strip, the top was the bottom at the same time. And so in this case, the Klein bottle is still a 2-dimensional manifold, but this time it's embedded in 4-dimensional space. So what makes the Klein bottle so interesting is that when you try to manifest it in 3-dimensional space, it looks like it's going through itself. But in reality, it's just not, it's not really recreatable in 3-dimensional space.
Well, technically there are Klein bottles that you can actually purchase online. And I've seen like a few videos on it, like in 3-dimensional space. But yeah, as you were saying, it's not like the exact same thing. It's just like our 3D representation of what it would look like. Because you can actually search for it and it's like an actual glass bottle.
Well, yeah, but it's like in reality, the bottle doesn't, or the shape doesn't really go through itself. Yeah. It's just the only way we can actually reproduce it in 3-dimensional space is if it literally has a hole and it goes through itself. But that's not mathematically how it goes down.
Okay, so that's pretty cool. Klein bottle is dope. Mobius strip times 2 pretty much.
Yeah.
And now we can talk about a personal favorite of mine. It's Gabriel's horn. Now, the reason it's a personal favorite is because you can actually do this yourself. Don't really need... I mean, I guess you could search it online on Google still, but it's actually very visual if you just know what the graph of y equals 1 over x looks like. That's basically it. So look at the graph of y equals 1 over x. Take only the positive numbers. So pretty much when x is greater than 0.
Well, here's what it is. It's It's y equals 1 over x
Yeah.
from 1 to infinity. Okay, so you're not starting at 0 because that would mean you're starting at
Yeah,
like,
okay.
an
Okay,
infinite height.
sorry. So technically you're starting at 1. Sorry, my mistake. You're starting at 1 and you're going to infinity. So again, hopefully you guys can visualize this. If you can't, as I said, you can just search it on Google. And okay, so once you have that graph of 1 over x when x is greater than 1, what we have to do is we have to rotate it on the x-axis or about the x-axis in a 360-degree form. That means if we rotate it, it would kind of look like a cone, or as the name suggests, a horn. So if we rotate it 360 degrees about the x-axis, that y equals 1 over x graph, we get this infinite looking horn, almost. And the really interesting thing about this is what happens when we are talking about its surface area and its volume. This object, this particular Gablier's horn, has an infinite surface area, but a finite volume. That means, now this is where it gets crazy. If we were to take paint, right? Let's say we were to paint this horn. If we were to paint the outside of this horn, we would never be able to finish because we would require infinite paint to paint the outside. However, if we wanted to paint the inside of this horn, we would need a finite amount of paint. Now, I think that is really cool. The fact that I think this.
I don't know if you explained that right.
No, I did. Believe me, my grade 11 math teacher explained it the same way, and believe me, it's 100% right because it has infinite surface area, finite volume, right? So the surface area, the outside, would take infinite to do, but if you want to fill the inside or the volume of the horn, it would take finite paint.
Yeah, that's not what you said, though. You said if you wanted to paint the inside.
Oh, no. I mean fill the inside. Sorry. I meant fill the inside. Sorry.
If you wanted to fill the inside, it would take a finite amount or finite volume of paint. But the distinction is that the outside surface area is the exact same as the inside surface area because the thickness of this a mathematical object is 0. So
yeah, sorry, once again, I did not mean inside painting. I meant like filling up. Yeah, I meant the volume part of it. But yeah, anyway, so I just think this is a really cool object that you can play around with. And if you know like basic integrals and derivatives, it's actually really easy to prove yourself too, because calculating volume and surface area, once again, if you know integrals, isn't that hard, especially for an object that's just been rotated across one axis. So it's not crazy hard to do. It's just a really interesting shape that I thought I should share.
And just like to simply explain the reason why one is infinite and the other is finite is because, well, one of the integrals, when you do it, it just doesn't converge to a number, and that is the surface area. It just doesn't converge to any number. It goes off to infinity, and the volume converges to a value of pi.
Yeah.
So it has pi units cubed of volume.
I think that's pretty cool too. The fact that it just pi. Yeah. And you know how pi is such an important number, and obviously it's just pi, right?
Yeah.
I think that's another cool thing about geometry. Not really anything to do with the episode, but just something really cool to add is that, you know, all these weird irrational numbers like pi, especially pi and e and stuff like that, you know, people underestimate how much its value is in math, you know? Like someone would see pi and be like, oh, you know, whatever, it's just a number, big deal. But the thing is, that number or this irrational number is maybe one of the most important irrational numbers in all of geometrical history because it's just so important when it comes to mathematical figures.
But here's one question for you, right? Mm-hmm. Do you think that there is a certain importance associated to every irrational number? Like, do you think every irrational number can find a place in math?
Wow, that's actually pretty cool. Well, okay, so I at least think irrational numbers in general, I think they're pretty cool. The fact that they, you know, they never end and stuff like that. But I don't think that every irrational number has something to do with math. You know, like there's special numbers, like for example, the speed of light. Is it a special number? Absolutely not, but it's still associated with something very special. Yeah. That's what I think the same thing with pi is. It's not necessarily a special number. It just has to do with something that's really special. That's what I think. Yeah.
It's an interesting take.
Yeah. Yeah.
So moving on to the next cool shape, it's called the Coke or Koch Co.
Yeah, snowflake. I think you should talk about this because I was looking at it and it looks confusing. I have seen this figure though. I have seen it before, but I wouldn't know how to explain it too well.
Okay, sure. So it's the KOCH snowflake, and so how you construct this shape is that you take an equilateral triangle, and then on each inner third of the three sides, you add another equilateral triangle, this time with side length of 1/3 of the original.
Mm-hmm.
And then you just keep repeating that process. So on each inner third of each side, you add another equilateral triangle. And then you get this shape that kind of looks like a snowflake, hence the name. So this shape also has a finite area, but an infinite perimeter because it's a two-dimensional shape. But if you do want to make it an infinite surface area, all you have to do is give a width to the shape.
Yeah.
So you make it like a three-dimensional snowflake, and it will have an infinite surface area but a finite volume. And it's the exact same idea as Gabriel's horn. So if you perform the integration, or not, it's not integration, it's more of an infinite series, because you're adding a certain volume for every iteration of triangles that you're adding to the shape. And so once you perform that, you will see that the volume actually converges to a certain value, which I don't have on the top of my head. I think it's something like square root of 3 times the side length squared.
I can tell you. So it's 11 root 3 over 135 pi. The volume. Oh, that's a solid of revolution. Never mind. Sorry. I was reading the wrong thing. So the limit of the perimeter. Where's the limit of the volume?
Well, no, they don't talk about volume.
Area. That's
what I was saying is that the area should be like root 3 side length squared over 5 or something
multiplied
like that.
by 2. Yeah, it's 2s squared root 3 over 5. That's the formula. Yeah. That's the formula. Yeah. And also a really cool thing about this is if you construct this thing, and I think a lot of people have actually seen this because I'm actually looking at it and I notice what it is, but I wouldn't be able to say its name. So I think a lot of people might have seen this before, where you can pretty much have an infinite zoom in and you see the same shape over and over again. And this actually comes up in a lot of geometrical shapes. It's just that this is one popular one. I think a lot of people have seen the ones with, okay, this might be really creepy to think about, but this is a famous one with the hand, and on each finger, there are 5 more hands. Yeah. And then you keep going down and you keep going down. And that's basically the same thing, right? It's basically the Koch curve, if you think about it. That weird thing that we see on Instagram every time. That's basically the same thing. Cool. Weird way to think about it, but yeah.
And one thing that made me think, or when you said when you zoom in, you see the same thing, I thought of the Mandelbrot set.
Okay.
Do you know what that is?
Would you care to explain?
Okay, so it's very hard to picture in your head, but basically, if you take it's basically a set of points in the imaginary plane. So the x-axis is the real numbers and the y-axis is the imaginary numbers. And then what you do is you pass each point through an equation. And I'm pretty sure it's like z equals z squared plus z naught, where z naught is the previous iteration, right?
Okay, I'm actually not 100% sure about this, but I'm just gonna be able to trust you.
Yeah, so I mean, you can just
Google it too. Yeah.
But what happens is that you get so all the points that explode to infinity, you color them in based on how fast they go to infinity, and all the points that stay within a local range of their initial value, you just color in as black. And then you get this crazy fractal pattern that if you zoom in on any point, you get a crazy fractal where like it repeats itself like an infinite amount of times, and there's like crazy like swirls, and it's just a really cool pattern. If you want to see like a really cool video about this, you can search up Numberphile. And if you want to see the actual Mandelbrot set, go on YouTube and search up Mandelbrot set zoom, and it'll zoom in on a random point, and it'll be really cool, I promise.
Okay. I think you actually have showed me this video. I believe you have, and maybe that's
Yeah,
what I'm thinking about.
I think I have actually.
Yeah, I think you have. Okay, so now on to something that even more special than Gabriel's horn, and no one will believe it's special when I say its name. Pythagorean theorem. Yeah. So whenever people hear Pythagorean theorem, they get these high school vibes and these high school flashbacks that, oh, I hated it, but it was so stupid. Where is it useful in reality? Nowhere, right? Well, that's clearly wrong because I'm here to explain. So, Pythagorean theorem, however useless it might have been in high school, believe it or not, when it comes to complex physics and general relativity especially, Pythagorean theorem becomes the most important formula, believe it or not, in physics. Let me explain. So general relativity, what's the purpose of general relativity? I think we have spoken about this before, but the purpose of general relativity is to calculate how much the space-time manifold, or the space that we are in, has curved. Let me explain. So the Earth, let's say, I think a lot of people have seen this demonstration with a carpet, and you place a ball in the middle, and how the ball depresses the carpet, and you can imagine the carpet as space, and the ball is the Earth, right? So general relativity, all it's doing is it's trying to calculate this curvature. How do we do that? That's the big question, right? Believe it or not, it's Pythagorean theorem. That's our answer. So what does that mean? So Pythagorean theorem is a regular right angle triangle where we can apply c squared equals a squared plus b squared. We know that, we live for it, and we've learned it a long time ago. With general relativity, however, because there are all these curves and everything like that, what they do and how they calculate the curvature of the manifold is they take a triangle, a regular right angle triangle, and see, obviously they have to do a lot of calculations, but they prove what the Pythagorean theorem would be. That means the a squared plus b squared equals c squared, what that equation would be on the curved manifold. That means how much ever this triangle, this right angle triangle curves, is the curvature of the manifold. If you see the first ever recorded answer to general relativity, which is the Schwarzschild metric, very, very famous, definitely do suggest you look it up. The Schwarzschild metric, if you look at it, it looks exactly like an c squared equals a squared plus b squared, but just with a lot more complicated variables, of course. So on the left side of the Schwarzschild metric, I'm obviously not going to go too deep into it, it's ds squared. And that can be taken as the hypotenuse. And that is exactly what we're measuring. So basically the point I'm trying to make is, believe it or not, Pythagorean theorem is one of the most important formulas or theories or proofs to understand and wrap your head around when talking about complex physics, especially general relativity.
I had to stay quiet for that because I just don't know anything about general relativity. So
it's really cool. It's really cool to think that, it all comes down to Pythagorean theorem.
Yeah, I mean, in basically every single branch of math, you're gonna see Pythagorean theorem. Like, you see it in linear algebra all the time, and you see it in calculus all the time. Basically, every time you're taking a derivative, you're using Pythagorean theorem, because rate of change is just right. It's the hypotenuse of the hypotenuse of dy over di or dy over dx.
Yeah, and I think that's what's also cool. I think I keep reiterating this, but it's really cool how all these fundamental concepts that we've learned, like in grade 10 and grade 8, and stuff like triangles, stuff like Pythagorean theorem from grade 10, stuff like that is so important. Like, it's the fundamentals. That's what's actually important when it comes to the long run. So understanding that, the fundamental stuff, especially if you're in high school listening to this podcast, understanding the fundamentals are a lot more important than you think they are. And I think that's what I have to say about the matter.
That is very true. And one thing that you realize is that like high school math becomes like pretty fundamental to first year university, but
Mm-hmm.
what happens is that you learn so much in first year that it kind of seems like first year is just the first building block of like the fundamental ladder
Mm-hmm.
for what you're about to go into. And like high school, it feels like it's like a Christmas tree, you know, like high school is like the trunk of the tree, and then first year is like the huge, like the first branch becomes like the support to the,
Yeah.
I don't know.
It all just keeps growing. It all just keeps growing is basically what you want to say.
I
Right?
just sound crazy right now
Yeah.
talking about Christmas
I
trees.
I think the basic point you're trying to make is that all foundations, everything you learn is important, and basically just pay attention to that.
Yes.
But yeah, that's basically what you're trying to say.
Yeah. So pay attention is the moral of this whole podcast.
Pay attention to your high school, kids. Pay attention.
I remember learning about triangles in like elementary school,
Mm-hmm.
and like we were drawing out triangles, and we were learning how like all the inner angles add up to 180 degrees.
Mm-hmm.
And I remember thinking like, yo, that can't be true, because if I change one of the angles, it'll be like more or less than 180 degrees. And then I had like this epiphany where I was like, yo, if I change one of the angles, they all change. And I was like, whoa.
Genius.
It actually does work. I had a mathematical epiphany there, and I was
In grade
sold
8.
for the rest of my life.
No, but I think that's also why Parker and I love math and physics just in general, because it all just kind of stems up from some fundamental that just makes sense, and then it just keeps, getting more and more complicated. So it's like the situation where if you don't understand 1 + 1 = 2 or 2 + 2 = 3, you will never understand 500 + 630, It's as simple as that. If you don't understand the fundamental stuff, like Pythagorean and all this thing, like understanding future stuff is just hopeless, because it all stems from this.
And like people who haven't learned integrals yet, they see the integral sign, they're like, oh, this is so complicated. But in reality, you're adding up rectangles.
That's literally all you're doing. It's not that complicated.
Calculating the area of a rectangle is just base times height. And in
Mhm.
integrals, you're just adding a bunch of rectangles where you're doing base times height. I mean, it's not as easy as I'm saying it to be.
Yeah, but it's not as hard as people think it is either.
It's not like crazy next level math. You're just, just finding an equation that will help you add up all of these rectangles together.
Mm-hmm. And
Yeah.
when we talk about geometry, we can also talk about different types of spaces. Now, unfortunately, we've already passed 30 minutes, so we might be cutting this a bit short. Maybe we can definitely have a part 2, talk about vector spaces,
Yeah,
different
for
types
sure.
of spaces. We can talk about different types of spans. We can talk about a lot of things when it comes to geometry. We completely disregarded the entire linear algebra section of geometry.
Yeah.
There are so many things we can talk about.
I think the part 2 of this episode is going to be linear algebra.
I think there are going to be part 2s to basically all of our
Yeah.
episodes, because as we're
Pretty
moving
much.
on, we're starting to notice that there are just so many more things we can talk about that we just haven't, that
Yeah.
we just, have to. So pretty much to all the listeners out there, you might be seeing a lot of part 2s coming up soon. Yeah.
All right. So I guess we can just cut it off here and then keep talking about geometry in the next episode, or not the
Absolutely,
very next
absolutely.
episode,
Yeah,
but
soon.
the
soon.
part 2.
You'll hear from us soon.
I think the next episode that's coming out is going to be an interview or like a conversation with a guest.
Oh, let's see. The suspense is killing me.
Yeah, so this has been episode number 13 of the Math and Physics podcast. I am your host, Parker.
And I am Ray, and we will see you soon.
See ya.